Welcome everybody, my name is Gábor, and I'm going to talk about how to use the public commercial Wi-Fi hotspots be used for free. As from my title, I am a senior research fellow at the Hungarian Department of University of Technology, and I have a 2701 lead auditor certification. I am a lead auditor at Vincot Hungary, and I am the managing director of Network Security Audit Limited. I'll talk to you about how to use Wi-Fi hotspots for free. It's just the exact opposite of what Gábor just told you. Here we are talking about how you as clients can connect to a network that you're not authorized to connect to. When I enrolled with my presentation at Hacktivity, I was not sure this may be of interest to you because this is a technique from back of 2007, and at the time I asked the colleagues whether there would be interest for this, and they said yes. I saw that earlier activities did not deal with this question. I thought it might be of interest as well. If you know what IP over DNS and knows the applications that can be used to utilize this, then you won't hear anything or much new. You may want to prefer to listen to another presentation in the adjoining room, maybe. So there'll be a legal declaration in my presentation. First, we'll talk about things that are not legal. I don't want to incite anybody to try this at home or live. Then we'll talk about IP over DNS, discuss why Wi-Fi hotspots are vulnerable and how this vulnerability can be exploited. And another very nasty method will be discussed, but I won't show any applications for that method because it's a real nasty method. So, legally you must be aware that if you use a pay-for service, then you're committing a crime. So I ask all of you to not try what you hear in this room. Don't try it in a live environment, and the presentation is not aimed at opening up available commercial Wi-Fi hotspots. The purpose is to provide information to network operators, because as I see it, many only learn too late about these things, and for this reason leave open these vulnerabilities on their own networks, and I think Hacktivity is a good forum to call operators' attention to these issues. What you will be hearing about is available online and can be installed on most operating systems directly. We are talking about publicly available tools. So what you hear in this presentation is not about something new. It's actually a summary of what is available, readily available. Some application names I have changed on purpose, and all of the methods that I'm talking about are at least 3 years old. We will not be talking about TCP/IP basics. Anybody here who doesn't know the basics of TCP/IP? None, right? DNS. I will talk about the essence of DNS. Conceptually, it will be necessary because if you misunderstand something, then you should still not misunderstand IP over DNS. And IP over DNS is a technically very interesting solution that will detail. We will not be speaking about Wi-Fi encryption, how you all have already experienced that public pay-for Wi-Fi networks are open. This is basically due to the fact that users, the majority of users who are not technically inclined, want to use something simple, so the connection must be made simple, so there is no authentication or encryption required for open Wi-Fi networks. We won't talk about the architecture of public commercial Wi-Fi hotspots. Let's talk about IP over DNS. Who has heard about it? Quite a few, about a quarter of the people. Who of you have used it? Two of you. The IP over DNS concept. Okay. You see a lot of IP over something, meaning that IP is transferred using on top of another protocol. The most frequent thing is passing IPv4 packets through an IPv6 tunnel, but DNS can also be used to transmit IP packets. DNS itself abbreviates domain name subsystem. It's actually a phone book or a directory of the internet. On internet, everything is done using IP addresses. So one IP address one IP station addresses another IP address, another station with a different IP address. Let's say I'd like to check index.hu, then I need to address it by its IP address. In reality, what happens is that there is an architectural DNS server, so every domain that is registered on the internet should be. We should provide for it an authoritative DNS server that is entitled to state things about this domain. Each subdomain has its own authoritative server. So if I have Jeney.hu, my name, then I must provide the authenticated server that can provide information about this site. There are also so-called top-level domain DNS servers that store information about the addresses of the various top-level DNS domains like com.eu, etc. This is the authoritative DNS server part, and the second part is the so-called caching DNS. This is the generally accepted terminology, and it means that each client on the internet needs to have a DNS server that it can query, from which it can learn what the IP address is for a given name, site name. We don't want to go into the protocol itself, but this is a simple challenge response or query response type of communication. The client asks what it should know about x.y.com, and then he will receive a lot of things about the IP address, the mail server, and quite a number of other things, like a textual descriptive text about that site. When in our browser we open Google's site, the operating system first looks up the IP address of the site called www.google.com. This is required for our client to connect to that server. Each operating system has its own internal cache, so the client first looks there, and if the cache doesn't have it, then it'll ask its local caching DNS server. There are two cases. The local DNS server has this information or it doesn't. If it does, then it will respond. If the cache does not have this information, then the caching DNS server needs to go further and ask the root DNS servers where to look for .com top-level domains, domain name servers. Then it gets back this information. Then it can query google.com's DNS server, address, and Google's server can tell it what its own IP address is. It looks a bit complicated, but it goes on pretty fast. On the other hand, this type of structure results in a very efficient operation. but it also makes the internet very vulnerable. You may have heard that the root domain servers in the top-level domain have been subject to hacking attempts multiple times. So we have the IP address, and we can build up the HTTP connection and download the HTML page that we want to look at. I have put up a very simple example. Let's say we would like to know something about the ncl.hu domain. Linux has a name resolution command that you see here. It provides the host's IP address and tells us what its mail exchange address is, so who will receive our mail sent to this domain. If we have a add -t, then we can receive additional textual information like the txt field contents of this domain. Once we have grasped this, we'll understand how we can use DNS to transfer IP packets. There are a number of fields. I've just shown you the txt field, but there are a number more. And this can be used for transmitting any type of information. First, let's assume that there is a phony domain, a domain that doesn't really exist. We only want to use it to transfer IP packets. Two things are important here before understanding the essence of the thing. First thing is that lots of coders allow us to convert any binary code to readable, to 7-bit code. So any binary thing can be converted to text like character streams. IP packets can be converted to DNS requests and DNS responses because, for instance, if I prepend before fake.com the textual information that I received when querying the IP address, and I request information about this domain, and the responding DNS server is not a real DNS server, but one that is able to perform this conversion, then the answer packets can be put into the null txt, srv, mx, and cname and fields to transmit IP packets. So what do we need for this? We need a domain where we can register such a phony subdomain, a fake subdomain. So this domain that we need is one where we have admin privileges. Also, we need a DNS server that will do this fake DNS name resolution. Or Bromine daemon is such a DNS server under Linux, and we need a client software which can translate in the other way around, which could be Bromine, also available under Linux. Obviously, when I communicate with my fake DNS server, I can set up a tunnel between the client and the fake DNS server, and that then transmits the packets. So when I want to send information to the other end, I perform this binary to text coding. I prepend it to the fake domain, and when I receive the answer, then I have to convert it in the backward direction. So I can communicate with the server by sending IP packets through DNS. Let me show you an example to make it more clear. We just used the host command before. Now I'll query the txt field, but in the fake domain whose name I have intentionally deleted, and I have entered an arbitrary character string. This is not a real text binary to textual output. It's just any character string, to which this fake DNS server will respond nonetheless. It will reply that it cannot process it, but we will see in the response that the descriptive text of this domain is this whatever that I am pointing to. So as I mentioned, under Linux, Bromine can be used for the purpose that we have. The DNS port number is 53, and the element Brom is element 35 in the periodic table of elements, and this is reverted to 53. This is where the bromine name comes from. It can do a lot of, quite a number of conversions. When you convert from binary to text, there are 3 options that are set automatically by the program. You can also set the automatically set the network size to scan. It also has a password-based authentication, so users, unauthenticated users cannot use the system. And I'm talking about Linux, but you can also use the software under BSD or Windows. So Bromine is running on the client. There is a Bromine D on the server, also running. Let's not forget that if you wanted to use it for internet access, then 2 things are possible. We can give a public IP address to the tunnel, and in this case, we can use on the client the IP address accessible on the server, or we must do NAT to allow the packets to get to the outside world, but there is a tunnel between the server and the client in both cases. Before looking at the example, let's look at how this can work on a pay-for Wi-Fi network. The first important thing is that pay-for Wi-Fi networks are available to everybody, and openness means that the client can connect to the Wi-Fi network, gets an IP address, and will control all the IP settings. But there is a central entity in the system, which is a gateway, and this gateway filters out users who are authorized to use the network, and restricts access for those who are not. In general, in most of the implementations, this works by the gateway running a web proxy function, so web requests from non-paying clients will receive a screen through which they can pay. You probably have seen it already. And also, packet filtering is normally used. So we shouldn't filter only information sent to port 80, but also other ports, and allow packets out that come from clients that have already paid. But there is one exception. This is the DNS queries, which are accepted from paying and non-paying clients alike. Why is this so? Why does this gateway allow DNS requests out from clients who have not paid? So as the colleague said, if we give a bad answer to the DNS request, then the client would cache our answer, and from that point on it would have this wrong cache information in the cache. So when the user wants to use this domain again, then he'll find it in the cache, and if that information is wrong, then the operator would be called continuously by the client, screaming at the operator that he has paid for the service and cannot use it. So first of all, there is a caching DNS that services the clients. This is either on the local network or some way further out, but actually DNS requests are started from this caching DNS and not the client. The clients only the client only queries the caching DNS, and the caching DNS is the one that will then try to find the route. So if the caching DNS is on the local network, then the information does not come from our computer, but from the caching DNS. So the gateway should have to look at the DNS query coming out. It knows that it comes from its DNS server, but it was sent by a user who has either bad or not, and I cannot determine this, or at least not easily. The other thing is that clients require real responses. Since clients cache this information, if there is no response, then they'll consider the domain as inaccessible, or if the DNS answer is fake, then they'll store it in the cache, and that will present problems. Once the client has paid, he will be unhappy because the web pages he wanted to view will not come up, and everybody uses their browsers with a lot of tabs open. So when they open their browser, a lot of web pages want to load. So we need to have DNS queries and answers through the network. So we can combine this fact and IP over DNS. So let's use this IP over DNS method to transmit information between our fake DNS server and our own client. Although these packets do not go get onto the network because we haven't paid, we don't get on that network, but our information will go out over DNS. So the fake DNS server can show anything that it sees from the internet. If you want to use this method, then you should first change your own MAC address so you cannot be identified later on. And very important, you should, so the local DNS that is set through DHCP, this should remain accessible. It is normally WLAN 0 on Linux. Everything else can go through DNS requests. Everything else can pass through that tunnel. The first question is how fast such a solution can be. Based on experience, 200 kilobits per sec is roughly the downlink speed, and about a fourth of it, 50, the downlink speed. And as I said, this is a technique from 2007, and many pay-for Wi-Fi networks are still open to this attack in Hungary as also abroad, and the speeds are also comparable. This tries to show you the operation of the thing. This is the client. Although it sends to the queries to the local DNS, it tries to resolve subdomains that we query for our fake DNS servers. So these queries will breach the fake DNS server, which in turn will answer telling the client the information it needs. This is a simple bash script to automate it. I'd like to highlight a couple of rows. Sorry, it won't show up too clearly. What is important is that if you use this tool, then you should first change your MAC address, and secondly, when you set the default gateway to the DNS0 tunnel interface through which DNS queries and IP packets pass through, and our DNS address should remain accessible through the original gateway. This is an application example. You started the script, we have a fake domain, which is a functioning server. The 208.67.222.222 is an open DNS server, that was accessible from the network from which I was conducting this test. So this was the local caching DNS of that network. And what we see here is that the upstream was coded using base 128, and as we'll soon see live, when we start the application, it first tries using a given fragment size, and if that size was appropriate, then it tries to increase the fragment size. If it was still okay, then it tries to still grow it further, trying to achieve the best bandwidth possible. If something is not okay, then it will step back. So we see that 188 was the size that was found to be optimal. I wanted to do a demo here. Okay, so here there's no pay for hotspot, but the organizers do have a hotspot on which we need to identify ourselves. But unfortunately, they already have patched this vulnerability, so I can't demo on that one. What I can show you, however, we have this open network here. I've connected to this Hacktivity Aruba open network. This is the WLAN interface. That has an IP address, a routing entry, and I have DNS settings. This shows that the local caching DNS is the 888 at address 8888, but it does not answer to queries. So now I'll start my script, but it won't be able to connect. But part of the process will still be visible. This is a minor script issue. I said it wouldn't succeed. And the connection, we also got disconnected. Okay, we do have connection, actually. That's interesting. It looks like it. Okay, we don't have an IP address. The problem is that I fiddled with the computer before I started this presentation. I have probably introduced a bug in the script. It didn't rewrite the routing table with the default route should have become 000 and it wasn't. Note that this is illegal, so if you do something like this, it is criminal activity. But there are cases when this may come in handy, because regardless, because even if you have paid for the for the use, you may still need this solution. One is when only HTTP and HTTPS traffic is allowed out, but you would like to do something else. In this case, IP over DNS allows you to access other protocols as well. If ICMP is allowed out by the operator, then there is an ICMP-TX that can also be used for this purpose. It can also be used as a VPN. Many people use VPN over IP over DNS, so a VPN is pre-appended, which allows the user to access his own network through a virtual network. How can you protect yourself against it? It's difficult to detect because although a lot of resolution queries come in for a given domain, but it's difficult to filter for the cause. There are a lot of applications that generate a lot of requests, and it is not necessarily IP over DNS application, but if you want to fight this or protect yourself against it, this exploit, this is how you should start. Second, the caching DNS should be put into the gateway, or there should be a connection between the two so we can know what the DNS query, so we know which DNS queries come from non-paying customers. And certain responses should be taken out in this case, but Bromine detects this. Or you can give fake answers with a timeout that is short enough, with a TTL that is short enough for the domain information to be requested again once the client has paid. The second method that I only would like to mention is a nasty one. A lot of scripts exist for it on the internet. Once we are under a Wi-Fi hotspot, then there are applications that allow us to discover the connected devices whose MAC address and IP address can be retrieved. Lost MAC. So we can impersonate the entire device, complete with IP address and everything else. This means that the person for whom you impersonated will be excluded from the network. When there is a collision between two erratic IP addresses and the IP addresses, then the connection will be dropped. So we want to transfer. We transfer information through the DNS. We do not harm anybody else. The service provider doesn't care whether he will service 120 or 121 users. There will be a minor additional traffic, but that will harm nobody. But in the other two cases we harm others. So I don't want to detail this. I don't even want to show scripts that utilize this. So as long as MAC and IP addresses can be freely modified by the administrator, this trick can be played every time. And if you can, then operate two networks, one for paying customers who get a key to the encrypted network, and once on that network they can have their real traffic. We need the encryption to not allow the attacker to get the IP and the MAC address, and even if he has before, he still does not have the key, so cannot connect. But unfortunately, the majority of users would not like this solution. They might not be able to use it. Nem hallatszik? Akkor jó. Ez egy eléggé gyenge verzió. Igen, látom, de ott egy bíves kolléga már hátul, ott fog ajánlatára. Jó. So, summing up, we have seen two methods that can be used to use public Wi-Fi hotspots for free. Let me stress again that this is not a nice thing to do. This is a crime. Never try this at home in your own interest. But the interesting thing is that although this technique dates back to 2007, a lot of Wi-Fi operators still have this attack spot open. I go to a lot of conferences throughout Europe, and I see that this method is still viable in most of the Wi-Fi hotspots. This basically has two reasons. One is that there are very few users who could utilize it, so operators think that it's not worth their money to close this door. But on the other hand, many of them don't know about this attack possibility, and this is why they leave their systems unpatched. And defense is not really tricky, so they could easily implement it. Thank you, and this is the end of my presentation.